So welcome back to 4820, INF 4820, Algorithms for AI and NLP. Our second of two introductory lectures to Common Lisp, the programming language for the semester. I am the other teacher, in case you weren't here last week. Next week, Mohaf will be back and will be beginning to take you on a tour of machine learning techniques. I ended up feeling that last week the pace was relatively gentle. I would like to think that most of you would agree with that, and hence I'm not going to do the usual previously on Twin Peaks 5-minute recollection of what we covered last week. Very high level, little bit of the history and significance of Common Lisp to the development of programming languages, symbolic expressions, the basic building blocks of Lisp expressions, which we break down into atoms, atomic as expressions, and lists. Recursion, a refresher, I hope, for many of you. How to suppress evaluation quoting, built-in list operations, which we use for code and data, and hastily towards the end, the difference between identity versus equality, and I'll come back to that midstream today. Today, more Common Lisp, pretty much all we need to know at this point to work on, to complete the first obligatory exercise, and soon start doing the programming that we'll want to do for the first machine learning topic. Specifically higher order functions, variable arity, writing our own functions that can take variable numbers of arguments in different orders, contrasting recursion with iteration, and one especially powerful iteration construct in Common Lisp, and a few more additional data structures in addition to lists. This is the one slide I failed to get through last week, so quickly. We've seen if already conditional evaluation. By that we mean that essentially we conceptually branch the computing. We test something and then we do one thing dependent on the outcome of the test or something else. You're familiar with that. We've seen if already. If takes 3 arguments. The first is what we call a predicate, a function that tests for something and whose result we in turn as a truth value, as a Boolean. And remember that nil, the constant nil, is false. Everything else in Lisp will be treated as true. Number p tests, has the p in its name. That signifies it's a built-in predicate. And then depending on the outcome of the test, we'll evaluate either this expression or this expression. These expressions are atoms, they're strings, they evaluate to themselves, so the if will just return either the string number or the string something else. In this case, what comes back, the value to which this as expression evaluates, is the string number. And that is conditioned on the test. Yes? Say that again. Ah, right. Yes, so you're saying during the exercise you wanted to have more than one expression in the then clause, for example, and you were unable to do that using if, because the condition then else in if are coded by position. The first argument is so these are 3 S expressions. If you put some set F here before the number, then that's an additional S expression. And because the condition and the then and the else are identified by their position, the argument number, that doesn't work. Fortunately, there's a more general special form for conditional evaluation. Cond is like a case or a switch. that you know from other languages. It takes any sequence of predicate expression tuples. It will evaluate the predicates, the first element in each of these clauses in sequence, in order. It will try this one first, then the next one, if this one evaluates to false. And then here I can actually have any number of S expressions. And so if you wanted to do multiple things, in case foo was less than 3, then you could have here a sequence of S expressions. Yes? No, you don't have to split them up with commas. So a sequence of S expressions just means you write them one after another. And because so there are various contexts where you can just write a sequence of S expressions. For example, we know one already, that's the body of a function definition. In the defun name parameter list, and then you can have a sequence of S expressions that will be the body of the function. That's familiar to you. You're used to having more than one statement in the body of a function. The same goes for the cond clauses here, because here the then, else, and so on are no longer identified by position. There's nothing in our way to put multiple S expressions here following the predicate. The first element in each clause is a predicate. It will be tested. It determines whether this clause is executed, well, evaluated, or not. So the general form, so this comes back for current value 42 with more general form if rigid, one predicate, one then clause, one else clause. I can drop the else clause, but I can't drop the then clause. I can't do an if and just have an else clause, because then the else clause would be in the second position and it would be interpreted as a then clause. So as soon as you want to do something that is not sort of vanilla if then else, cond gives you much more control, more flexibility, and this is the general syntax. And in fact, I could put a plus here. I can have more than one clause here. I should put a plus here, in fact. Yes. Right. So T we encountered in passing last week is a symbol that has a predefined value. It evaluates to itself, and it's the constant that we conveniently use to denote the truth value true. So it's Boolean true. And what this does, I put the T here in the place of the last predicate, and that means this is a predicate that will always evaluate to true. Good question. And hence, in this cond, I don't have to do that. It's just an idiom. So often I want to make sure that something gets evaluated. And if all of the other predicates fail, then this will be the default clause. Yes? No. As we do here. I don't think that's valid common Lisp, actually, as you say it. Could someone check that, please? I think this is scheme. So here I think we're seeing, so this is scheme. Those who've taken the scheme class and in their bachelor's recognize this. I don't think this is common Lisp. Mohov, could you quickly check that? Can I have an else in a cond? I believe not. I think this is spillover from scheme, and this should be T here. But I might be wrong. I always put a T there. But yes, it would be the same if else were legitimate common Lisp. No. So if the question is if after one, I'll generalize your question. As soon as one predicate, one condition succeeds, will we evaluate any others? The answer is no. So this is also conditional evaluation. We sort of test something and then we go down that branch of the computation. And that means as soon as we hit the first predicate here that returns true, we execute, we evaluate the sequence of clauses that are paired with it, as you would do in a case or a switch statement in any other programming language that has those constructs. And that, the last clause here determines the value of the cond expression as a whole. So the cond expression is evaluated as any expression. All expressions receive their semantics in terms of the value that they return. And so the cond will be evaluated to the value of the last clause in the first predicate that returns true. That was a mouthful, but that is exactly what it does. Yes? When will the default clause be returned? So under which conditions will I come here, you're asking. And given what I just said, you should be able to answer that. So any of these all of these must return false, because only then do I come down here, and then this will be the first predicate that evaluates to true, and hence that's when I get here. Do we have an answer on else in Common Lisp? Not yet? You want to be sure, as is your nature. Okay, let's move on. Let's not get carried away by the syntax. This is just using parenthesized expressions to sort of unambiguously write out what are the predicates, what are the corresponding clauses that get executed. You are reading the Seibel Practical Common Lisp book, aren't you? So that goes through all of this in greater detail, and truth be told, I don't want to sort of get carried away in the lectures with surface syntax. Since Lisp has such a simple, easily accessible syntax. So, now let's move on to something fun. Something that characterizes the family of functional languages. Before we do that, let's reflect a little more on symbol semantics. So we said symbols evaluate to the value that has been bound to them. That's what we have said so far. So pi is a predefined symbol, and it has a predefined value of 3.1415 and so on. I type in pi into the interpreter at the REPL, and I get back the value. But in fact, in Lisp, symbols can have two values. They can have a value and a function value, or a variable value, let's say, and a function value. So when I do def parameter or setf, as we did last week, I assign a variable value to the symbol. I can, in addition to that, use defun and bind a function value to the symbol. So that's the sense in which Common Lisp is what is called a Lisp2, contrast to Scheme, for example, Closure, which are Lisp ones. They take away this flexibility, if you will, of a symbol naming both at the same time a variable and a function. And from context, it will always be clear whether I actually talk about the variable or the function. But still, it's going to be rare, I think, in our programs that we actually want the same symbol, the same identifier, to be both simultaneously the name of a variable and a function. But we can do that. And so that means, how do I access the function value of a symbol? Because when I evaluate the symbol, I get the variable value. And to access the function value of a symbol, I need to introduce, I think it's our fourth special character. And that is the hash mark quote, or sharp quote it's often called. And that gives us the function object bound to a symbol. So here I say defun foo, so I establish foo as the name of a function, then I do def parameter foo, the same symbol, establish it as the name of a variable. So now foo is two things. It's the name of a variable and it's the name of a function. I do foo of foo, and I get so this foo is the variable, it evaluates to its value 2. It's passed into this function and multiplied by 1,000. This is a typo. Surprising we still catch typos in these slides. I think we, depending on the outcome of else, I think that's our second typo already. So this was surprising, wasn't it? I say def parameter foo 42 and it returns 2. That was actually testing whether you guys are with me already this morning. So do better next time, please, for my own benefit, in case there are more typos coming up. So foo actually has 42 as its value, and hence 42 times 1000 gives us 42,000. I evaluate foo, type it in, ask for its value. I receive the variable value. How can I get the function? I need to write hash quote foo, and what comes back is sort of not especially readable. It's Lisp's way of telling me this object is the function that is named foo. How can I put a function up? So this is a function object, we'll soon see that functions are values. They're objects just like any other values, like numbers or strings. How can I put a function object to use? I need a function to say, take this function object and apply it to this value, and that function is called PhoneCall. So PhoneCall takes as its first argument a function object and calls it on the remaining arguments. Yes? It is possible to further inspect that function. You can even disassemble it and look at what the compiler did to it. Yes, so all of that information is available. But this is just the printed representation that the read-eval print loop uses to tell us that's what it is. If you want to know more about it, ask me. So you can inspect this function object. Just as remember, the simple quote was a shorthand notation for the special form by the name quote, Q-U-O-T-E. The same is true for hash quote. No, sorry, forget about that. That is true, but that's not what I'm wanting you to tell you. So the pair of the combination of hash quote and PhoneCall, and then there's also apply, which is a variant of PhoneCall, are what we'll use to pass around function arguments, function objects as arguments, and invoke them under our own control. So that's what is sometimes called, well, that's what gives us this definition of higher order functions. We'll call a higher order function any function that either accepts functions as their arguments or return functions as their values. So higher order functions are functions that operate on functions, you might say. That's the sense of higher order. And for that to sort of work out nicely, it needs to be the case that function objects, are first-class citizens. They are objects just like numbers, strings, anything else. I can create them at runtime. I can pass them around as arguments. I can return them as values. I can store them in variables, just like any other type of data. Here is a classic in functional programming, a function filter that will want to accept a list and some arbitrary test. And we want the filter to, well, act as a filter. Return us from that list all of the elements that satisfy the test. So test here needs to be a function object. And I use cont here. In case list is the empty list, then the result is the empty list. And next I invoke the test function here on the first element of the list. And when that succeeds, I say that first element of the list is a part of our result. We need to preserve that in our output. And to do that, I say, well, I const that first element, which I want in the output, onto a recursive call filter on the rest of the list using the same test. So recursively, I work through the lists. I test each current first element with the test. When the test succeeds, I keep that element in the result. Otherwise, so here we are in the else clause, the default. I just call myself recursively, and the result will be that the current first element disappears. Because the result of this filter function, so here's an example call, foo is the list containing those 5 numbers. I filter foo using hash quote even p. Even p is a built-in predicate, tests a number for evenness, the opposite of oddness. I need to say hash quote here because I want to access the function object that is named by the symbol even p and pass that object into the higher order function filter. What comes back is a list containing only those 2 numbers that satisfy that test. So what I have here is a function that is very flexible in that I can parameterize it simply by picking whatever function object here defines the selection criteria that I want to apply in extracting elements from that sequence, from that list. Yes? You have to use the PhoneCall here because test is a function object. So what else would I do? And write test here. So you are asking, why can't I do what you may have done in Scheme? And in the second clause, just say test of the first of list. And then do the consing. That's what someone who has used Scheme, that other Lisp dialect, which is what is called a Lisp 1, where a symbol can have either a variable value or a function value, but not both at the same time. That's what you would do in Scheme. Sorry. Yes, so this paren here is just part of the cont. So I put the symbol test into the first position of a list. So we write it like this. We invoke the function. We come to the point where we test this predicate. What will happen? We evaluate a list, so we invoke the standard rules of evaluation. Those ask for evaluation of all of the arguments first. So I evaluate this argument, that will return the current first element. Now it's time to call test. Standard rules of evaluation say the first element got to be the name of a function. So is it the case that test is the name of a function? It is not. Test is a local variable. It's a parameter to the function whose variable value is a function object. So that's different. I call a function, the parameters become local variables. Crucially, they become local variables in the body of the function when the body of the function is evaluated. Hence, the symbol test functions as a variable here. And it has a variable value, and that variable value is a function object. I can see how that is potentially confusing. But there's nothing confusing about it once you reason formally over it. And hence, this will give an error. It will say test doesn't have is not the name of a function. It doesn't have a function value. Because it would only receive a function value if I had said defun test somewhere. So if I can say def parameter test hash quote something, and that would change the variable value. It would make that value a function object, but that doesn't make test the name of a function. So that's a subtle but important difference. Hence, yes, we need to use PhoneCall. And this was hopefully a useful clarification. Say that again, please. To the PhoneCall definition, I have only showed you an example of PhoneCall. So PhoneCall takes two arguments. No, PhoneCall takes a variable number of arguments, but the first one has to be a function object. And then it calls that function object on the remaining elements of that list, and those remaining elements become the arguments of that function object. And that's what I do here. Again, I have a function object, and it only receives one argument. But I could use PhoneCall with functions that accept more than one argument. Yes. You're saying PhoneCall basically takes the name of something and tries to evaluate it as a function. That's not quite correct. PhoneCall takes a function object as its first argument. No. So that's different. The name of a function is a symbol. The function object is an object. That's something that Lisp will print like this. And PhoneCall takes a function object here. In fact, I believe PhoneCall is so robust you can also just give it the symbol and it will look up the function object because it's obvious what you're trying to do. But the definition is you put a function object here. And hence the hash quote here says foo is the name of a function. Please give me the function object that is the function value of that name. So the hash quote here, as we saw here, returns a function object. Alrighty. So what we have here, to summarize, is functions, obviously, that use recursion. So we're putting many of the pieces together. Conditionals, conditional evaluation, predicates. And we're using lists, both for the code and for the data here. So an example of sort of many of the high-level characteristics of Lisp that we have introduced so far. Okay, a few more examples on higher-order functions. It's often convenient to invoke, to define a function object without binding it to a symbol, without giving it a name. That's what is called an anonymous function. And we build anonymous functions using this special form lambda. And the syntax of lambda is parallel to defun. The one thing that is missing is the function name. So lambda parameter list x body will create an anonymous function, an unnamed function that takes one parameter. It will call that x when evaluated, and it will evaluate this body when called. So that's parallel to defun in terms of syntax, and I can use an anonymous function as the test argument to our function foo, our function filter. So same foo as before. Now I want to select all of the elements of that list that are both greater than 20 and less than 50. And this is mildly silly example, you might say, demonstrating the flexibility of parameterizing the filter function simply by virtue of passing it a test function object that defines the condition that we want to enforce in filtering. And I don't even have to define that function because presumably this function here a predicate that tests a number to be both greater than 20 and less than 50 is not a function that I will find very useful in the rest of my program. So I need it here and only here, and hence I don't define it. I don't have to define it. I can use it as I can temporarily create it as an anonymous function using lambda. So typically used for ad hoc functions that are locally relevant, sort of one-off functions. It also makes the code potentially more readable, because the exact test is here where I use it. If I did defun greater than 20 and less than 50 as a separate function, I would potentially have to look up how that function is defined. So here I locally have accessible the information about what that anonymous function actually does in line. And I can also use lambda when I want a function to return another function, a function generator. Then I can put hashcode lambda as the last S expression into the body of another function definition. And then that function becomes a higher order function in the sense of returning a function. Functions are first-class citizens. They're objects just like number. And here Lisp betrays its origins from the work of McCarthy to formally define computing. But this ability to use the lambda calculus to define anonymous functions has since, I mean, it's taken a few decades, but Java has recently adopted anonymous functions. Python is sort of halfway there, or mostly there, I think, by now. This is such a powerful abstraction that it has sort of penetrated most contemporary programming languages, even where they maybe didn't have it in the original design. This is part of the core assumptions. So this was part of Lisp before Lisp actually accidentally became a programming language. It's part of the foundations of Lisp. So how do we return function? We've seen how we've created an anonymous function. Here we define a function generator, a function that will return another function. And the purpose here is carrying on that slightly silly example, or maybe not so silly, where I assume I have a sequence of numbers and I want to use filter to extract those numbers that are within a certain interval, within a certain range. And let's say I actually find that I have to do that very often. First I need to filter for the range from 10 to 50, and then for the range from 50 to 200, and then for the range from 200 to, and so on. And hence I find it convenient to not have as many anonymous functions that all would be very similar except for the different lower and upper bounds of the range, but rather I give myself a function generator, make range test. It takes the lower and the upper bound values, and it returns an anonymous function that is exactly that kind of function that I can give to filter. It takes one argument and it tests for both greater than lower and less than upper. So make range test now is a function, takes two arguments, that returns a function, and what it returns is what I can use as the second argument to filter, as my test function. So make range test is what we call a what do we call the class of functions that return functions? A higher order function. Thank you. Make range test is a higher order function. And we know that filter is a higher order function because it takes a function as its argument. So here we have the interaction of two higher order functions. And I said last week, Lisp has a large built-in standard library, and it excessively uses this technique of parameterizing built-in functions from the standard library using higher order functions. And we'll see a few more examples of that. But this is the mechanism that Lisp uses to gain a lot of flexibility in how you can use its built-in functions from the standard library. Many of them have often optional arguments, which are function objects, which will parameterize, that is, make, customize the result of the built-in function. And speaking of optional arguments, we said last week that the syntax of Lisp makes it very easy to write functions that take a variable number of arguments. That's because the name of the function precedes all of the operands, so I don't need any special syntax. How do I define functions that take variable numbers of arguments? There are multiple mechanisms to do that. One is to declare some parameters as optional. And to do that, I inject into my parameter list with defun or lambda the special symbol &optional. What's a predefined symbol? That just means from here on, the remaining parameters are optional parameters. So x has to be there. Everything else can be there, but doesn't have to be there. So y can be present. And then here, still within the parameter list, I have something that is a pair. And this means there's a third parameter. It's the second optional parameter called z, and it has a default value. So when not provided, then z will take the value of 42. A few examples, or let's first observe what this function actually does is it just returns so that we can see what has happened, the values of x, y, and z in the body. Let me just get through this and then take your question. So I can call foo on one argument, and what comes back is the value of that argument. This was internally which parameter? X, obviously. And then y is optional. I didn't provide any argument for parameter y. Didn't provide a default value. The rule of thumb in Lisp is when no default value is given, it's going to be nil. So everything that is not explicitly specified defaults to nil. That's a very good rule of thumb. You take the first of nil, Lisp will say nil. The first of the empty list. And then z wasn't specified either, but there we declared its default value, and that's what we get back. I can call foo on 3 parameters, or on 3 arguments. So often we say that what I give to the function when I call it, those are the arguments. What the function declares in its parameter lists are the parameters, and when the function is invoked, the parameters are bound to the arguments, and they serve as local variables in the body of the function. And so here I get back 1, 2, and 3. You had a question. Good. So you're saying I have 2 optional parameters. How can I make it so that I actually call it with something for z without y? And using this mechanism, that's strictly speaking not possible. Because the assignment, the identification of the parameters is by order. And that is the third parameter. So if you want to give it something for z, then you'll have to give it 3 S expressions following the function name when you call it. But of course, you already observe, since it will default to nil anyway, I can put that nil there. That won't change anything. But I mean, formally, you are providing a value for y. It's just, well, yeah, it's nil. You had a question. In calling it, so foo with 1, 42, and nil? Yeah, or the empty list. What would come back? Yes. The empty list can be the element of a list. So in that case, Z would have as its value the empty list. And what we would get back is 1, 42, and the empty list, all in one list. So the third element of that list would be an empty list. Okay, your question already sets us up to introduce another mechanism for parameter optionality called named parameters. Also, in the past 10 years or so, becoming more standard in many programming languages, where I can say, I don't associate arguments with parameters by position, but I actually do so by naming them. And the special symbol here that I need in the parameter list is called &key, because these will be called key parameters, because there's a key, there's a symbol which is the name of that parameter. And the body is the same, but now this call hasn't changed, so key parameters are also optional. But when I actually want to refer to them, I need to prefix each argument with the name of the parameter and writing those names with a colon. So here's our 5th special character. I think 5 is still. The colon, when I put it in front of a symbol, makes that what we call a keyword symbol. So colon Z is a symbol, and specifically it's a keyword symbol, and keyword symbols evaluate to themselves. And it's these keyword symbols that I use in combination with keyword parameters to take into use this mechanism of naming parameters. And since I'm now no longer identifying them by order, by position, I'm free to actually put Z before Y. Or I would be free to just talk about Z. What happens if you combine optional, optional, and &key? That's well defined, but it makes my head hurt. It's not something that I think you will typically find useful. Because &key implies &optional. So in fact, you can have optional Y, &key Z. So that would be, and maybe you sometimes do that. So you want one parameter obligatory, one that can be there by position, optional, and then more optional, more keyword, so more optional named parameters, which are keyword parameters. These are just 2 mechanisms, and we'll find both in the standard library, hence we need to be able to understand them. That's why I introduced them here. The final mechanism that also gives us variable arity functions are so-called rest parameters. So that's the 3rd special symbol I can put into a parameter list. And that will, into a single parameter, collect all remaining arguments. So here I say an average function. It takes at least one argument and then any number of rest parameters. And what it does is, so we want to compute the average of an arbitrary sequence of numbers. And what it does is first it puts x onto rest, so it constructs a list numbers, that is the list rest plus x. Then it says sum together, so it applies the plus function. So hash quote plus is the function object from the predefined function plus to this list of numbers, and then it divides the sum of all of the numbers over the length of that list. So that's going to be the average. And it actually works with just one number, because then rest, this list will be the empty list. This list will contain all parameters that follow the preceding parameter specification. In this case, only one obligatory parameter. So in this call, rest is the empty list. I cons x is 3 onto the empty list. That's a list containing just 3. I can sum together. We observed that plus I can call with just one argument. It will return that argument. And the length of this list is 1, so I divide 3 over 1, and the average of 3 is correctly 3. But I can call it with any number of arguments. 1 will be the value of x. The list starting from 2 to 7, these will be collected. So 1, 2, 3, 4, 5, 6 remaining arguments all end up collected as a list and bound to the parameter rest. And that's how this works. Let's take one final question and then take a break. Yes? So why, yes, so do I need the x before the rest? Why do I define this function like this? Any suggestions? Yes? Exactly. So in crafting, in designing my parameter list, I make a decision about the range of the number and range of parameters that the function accepts. If I didn't have, so putting an x here, that is not optional, that is not key, that is not rest, means this function needs at least one parameter. And ampersand rest means, in addition to that one, any number. Without this, it would be a function that I can call with 0 arguments. It would have an arity of 0 or upwards. Arity means number of arguments expected by the function. And if I did that, then I could say average, open paren, average, close paren, which would mean give me the average of the empty list of numbers. And that's not well defined. The way I compute here, in fact, I would end up taking the length of the empty list, which is 0, and I would be dividing by 0, which would give an error. So the one obligatory parameter protects against that error. It means the average function is only defined for one or more numbers. Let's take a break here and come back in 15 minutes. Welcome back. I think we went through these various mechanisms that just give flexibility in terms of defining functions with variable numbers of arguments, named or unnamed, collected into one list or not. I'm inclined to move on, come back to what we very briefly said last week about equality. That's a fundamental question, of course, to human existence as well as to programming languages. What does it mean to be equal? A very central, important, foundational distinction is that between identity and equivalence. I've never tried this before. Maybe the human equality, I can even stretch that. So twins, from the same egg at least, you might say are equivalent. They have the same features. They may be difficult for us to tell apart. Whereas there's only one person that is identical to me, and that is not my twin brother, that's me. Not sure that analogy is the most helpful. So in terms of objects, Lisp objects, there's a distinction between object identity, the same thing, at the same location in memory, or two things that are equivalent, that have the same structure, say two lists that have the same number of elements and all of the elements are equivalent. And that's the distinction between EQ, the stricter test for identity, and equal. This matters because EQ identity is much faster to test. That's essentially a pointer comparison. And here we had observed that when I type in a quoted list, that gives me an object. We know that gives me 3 cons cells that point to the first and the rest. We could draw them. When I use the list function with 3 arguments, that also constructs a list. Well, that's a separate object. And these two are different objects. They are not EQ, but they are equal, because they're both the lists that contain the numbers 1, 2, and 3. But they're two different instances of that list. So that's the distinction between identity versus equality. That's important to put under your pillow and never ever forget. This is not about Lisp. This is foundations of programming languages, or foundations of computer science. Now for efficiency, EQ is actually not defined on numbers and characters. And for those, I need to use EQL instead. So when I want to compare equality of numbers or characters, then the right equality predicate to turn to is EQL. And here we see that there can be, and numbers are like the moon. There can only be one object that is the number 42. That's the moon in our solar system. No, well, the moon in our Earth-centric perspective. The sun in our solar system. There's only one object that is the number 42. So I can type it in as many times as I want. They will always be equal. But of course I can have different data types for the same numeric value. So the integer 42 and the floating point number 42 are not the same. They're not identical. When I want to stretch comparison to be the most generous, then there is a fourth variant, equal P. So these are ordered in terms of strictness. So EQ is most strict, and equal P is most forgiving. Then equal P will even try to coerce the data types. These are two numbers of different types. It will try to coerce the integer to a floating point number and then ask, do I end up with the same numbers? Strings can be EQ, but when I type in two string literals, so anytime I use a double quote and put something between two double quotes, that's what is called a string literal. That's an object. And these two strings that I just type into the interpreter, they become two different objects. They are not EQ, but they are equal. Because strings, we will imminently learn, are sequences of characters. Again, equal P, the most forgiving variant, will when applied to strings, do a case-insensitive comparison. Take home, well, and there are many type-specialized tests. We've seen the equal sign. Type-specialized means that they are only defined to work on certain types of objects. For example, the equal sign is only good for numeric comparison. You can only use that with numbers. String equal, I can only use with strings. Equal I can use with any type of object, but effectively what the Lisp compiler needs to do is needs to generate code that says what type of object are we looking at currently, and then invoke the appropriate comparison. Hence, when we care about efficiency and we know x and y will always be numbers, then it's going to be, I think, both more readable in terms of the code and potentially more efficient in terms of how fast it runs if I actually use the comparison predicate that is specialized for this data type. For example, equal for numbers or string equal for strings. So take-home lesson, I never use equal P in my own code. I can't really remember where it sort of tries to be forgiving and what kinds of accommodations it will do. So if I wanted to compare integers to floating point numbers and wanted same numeric value to compare as true, I would probably write my own equal predicate for that. But that's up to you. These are the sort of 4 common equality predicates that are somewhat type, or that can be used across different types of objects. We'll need to keep that in mind. Here is a suggested home exercise which you can, which you could do at this point. At least the first half. This is from an early exam. Write 2 versions of a function swap, one based on recursion and one based on iteration. We haven't talked about iteration. That remains to be done rest of today. Function should take 3 parameters, x, y, and list, where the goal is to replace every element matching x with y in the list. Here's an example of the expected behavior. Swap string foo for the string bar in this list, and then what comes back, wherever there was a foo, there's now a bar. I'd recommend you, so please don't use destructive operations, I'd recommend you try writing that. And as you do, you will come to the point where you have to pick a comparison predicate to test 2 strings for being the same string. So that's where you would have to make a conscious decision about so what do we, I should take, where you need to put your own interpretation into this, what we say here, every element matching x with y. What does it mean to match? And then as sort of for extra fun, maybe enhance that function and add a keyword parameter where you give it the equality predicate. And that would be very much in the spirit of the Lisp library. But we need to move on because we have 2 more topics to cover. One very superficially and briefly. But it's important that you're aware of one property that most people still agree is unique in this generality to Lisp, and that's its macro facility. And by macros we mean programs that generate programs, that is Lisp code that manipulates Lisp code. And because code and data is represented in the same syntax as expressions, parenthesized lists, prefix notation, sort of playing with that code versus data divide is very simple in Lisp, very straightforward. So a macro is code that manipulates itself, that is Lisp code, before it is passed to the compiler. And we can use that to either implement special forms, to diverge from the standard rules of evaluation, or we can even use it to extend the syntax of the language, and we'll see an example of that shortly. Control or prevent the evaluation of arguments, that's what we have so far seen in special forms. So we have called if, cont, defun, setf, and, or special forms, because what does it mean to be a special form? What's special about defun? It's not a standard function, and it's not a standard function so that it doesn't. See, did you say it doesn't work like a list or like Lisp? It doesn't work like a list. It doesn't work like a list that encodes a standard function call. So for standard functions, the standard rules of evaluation apply, and those call for evaluating all of the arguments, then call the function. And for defun, that is certainly not what we want to do. We don't want to evaluate the function name. We don't want to evaluate the parameter list. We write the defun for the sole purpose of defining that function, of associating that parameter list and that body with this function name. And hence, it needs to be freed from the standard rules of evaluation. Because if I just type it in and if it were a function, then all of the arguments are evaluated before that function is even called. And that's what special forms are. And the special forms we have seen so far, they are in fact implemented as common Lisp macros. So macros are the escape door from the standard rules of evaluation. We won't be teaching you to write macros, but if you feel game, it's a very useful and nice facility that is especially well developed in Lisp. And we will be using, possibly excessively, one macro that extends the syntax of Lisp. And that's what I'll introduce next. And that's a construct for something we haven't taught you so far, iteration, something you're really used to. For, while, do. And even though Lisp as a functional language in the functional tradition sort of emphasizes recursion where it's a good fit, there are problems that are just very natural to solve in a loop, in an iteration. And we're not purists or missionaries. You get to pick the tools that do the job. I use loop a lot in my own code. There are two specialized simple iteration constructs, do list, do times. Just briefly to introduce the concept of iteration. So do list X, that list, and somebody here means go through that list, bind the parameter X to each element at each step. So for X in would be a paraphrase. And execute this stuff here. When X is even P, then push X onto result. Result is a local variable out there that I've bound in a let form. So this is exercising some of the pieces we've introduced last week. Finally, return the reverse of result. That's because push, if you look it up from last week's slides, makes X the new first element in result. It's setf result cons X result. It's a macro. And so this is one way of going through that list and extracting a list containing the even numbers. Something we did using filter before. Do times, another built-in iteration construct. It's counting essentially. So do something with X in the range 0 to 5 probably. I don't even remember. I never use do list and do times anymore. I use just the one iteration construct loop. I think this is 0 to 5. And then, so that would be 6 iterations, 0 to 5. The same thing, and put those values of X that are even onto that list. So do list, do times, they're there when you have something very trivial and don't want to use the almighty loop. You can put them to use. But here is the thing that is much more general and more flexible, and that makes do list and do times at least unnecessary. As in all programming languages, there's more than one way to do it, and you get to pick what rocks your boat. But there are many things you cannot do using do list or do times, but that you can do in loop. And loop, I like to say, is like poetry. It's English poetry. For example, what we're doing here is the equivalent of this one here, and so we could say for X below 6, when even Px, collect X. Don't have to do push and reverse. I can just sort of write it down the way I would like it to happen. And here there are some keywords: for, below, when, collect. These are part of the loop syntax. And these take as expressions as their argument. S is going to be a local variable in the loop. below 6, that's the upper range. This is a predicate. This is the same x. So iterate x up to 6, and for all even values of x, collect them in a list. It's pretty much what we say here. It's almost like English. A few more examples. So I can do this stepwise iteration. Most of the loop constructs have an iterator variable for I from initial value to final value by some step, and the from is optional, the by is optional, but I need the to. So I could just write for I to 50, and that would count from 0 to 50 in steps of 1. But I can say I want a different step, or I want a different initial value. Collect just means return a list with all of the values of this as expression. So here I could write square of I, or something much larger. I could call another function. And everything in red except the 50. The 50 should be black. So that's, I think, the third typo for the day. Are parts of the loop syntax. So loop extends Common Lisp, the syntax of Common Lisp, in a very broad way. It's essentially a mini language for iteration. There are many variants of loop. The criticism is at times that it's not perfectly Lispy. It doesn't have enough parentheses. But I find it more important that it's quite intuitive and very readable when you indent it properly. So Paul Graham, one of the Lisp advocates, pioneers, says he doesn't like it. One of the worst flaws in Common Lisp. Not my point of view. I use it a lot. It's extremely general and powerful. It is Lispy in the sense of trying to design and implement the most general possible solution to a problem. So to do it right. That's the Lisp philosophy in my view. And I think the loop macro accomplishes that. If you compare to all of the other programming languages that you've learned, I'll be surprised if you'll find one that has one sort of parameterizable iteration construct that can do everything that you can do using loop. A few more examples. So far we were just saying collect I, but so we have some iterator variable, we have some specification of how often, where we want to start, when we want to finish, and so on. We can control what happens at each iteration step, and we can change what we actually do to compute the result. So collect would mean return a list, return a sequence with some sequence of computations, but I can also sum them, or I can max them, then I will just return the largest number, or I can min them. So there's variation about this action statement here. I'm not limited to numbers. I can also loop across a string, and that will give me a list containing all of the characters. So here we see the 6th special character. No, we've seen the sharp sign essentially. So sharp backslash, that's the representation of a single character. So this is now the list that contains the characters FO and FOO. I have destructured the string foo. I can combine them. I can have local variables inside of the loop. So with foo equals something, that's like a let around the loop. For I in foo, that means in, go through the elements of that list. For j from 0, count from 0 upwards. So now I have 2 for statements in one loop. Nothing to stop me. I'll have I in each iteration an element of the list. I'll have j in each iteration a number. When will this terminate? For j from 0, if we just write that, that will never terminate. That will keep counting. But for I in foo, iterating through the elements of a list, that will terminate when I'm at the end of the list. So in this case, This is the for statement that determines when we terminate. And actually here I make explicit that without the until, I would iterate through all elements of the list. But I can also explicitly say stop the first time I becomes equal to the symbol C. So that means when I reaches this position in the list, the iteration will terminate. I will never take the value of the final value. And now I do format, that's printed output. That's on my last slide today. And this just means print something here, and a new line, the values of j and I. And so here I see that I do 2 iterations where I is counting from 0 and, sorry, j is counting from 0. I is the first 2 elements of the list. When I becomes the symbol C, the loop terminates before this do. So do is another action statement in the same subfamily as collect and sum and so on. Yes? Which part? Here, because symbols are not case sensitive. So lowercase a and uppercase a as a symbol are the same thing. Strings are case sensitive, but symbols are not. And so they are identifiers. And by default, they print in uppercase. So Lisp decides that the canonical way of showing a symbol is uppercase. Most programmers write them lowercase, but the canonical printed representation is uppercase. I think I have even more examples, but I feel I would maybe, I think you can play with this more by yourself, maybe do some of that in the laboratory session tomorrow or next week. Loop is, there's a whole chapter, in fact a chapter and a half in Cybele. Loop for black belts, I think, is chapter 20 or so. You might not need to read all of that immediately, but it's something very useful to sort of go back to and see. I want to do something iteratively. I was told I should be able to do it in loop. Let's see how to do that and whether that is true. I'm fond of Python. How would I do it there? Let's compare. It's a legitimate approach to the problem. So loop is an attempt to give you the Swiss Army knife of iteration. And to learn the language, you need to know the different for variants, collect, do, sum, until, finally, and so on. You need to know the words of the language, and they are what is in red here. I think that, well, almost. We'll introduce hash tables, and loop, of course, can also iterate over the elements in a hash table. It should be able to iterate over anything that one might want to iterate over. Is it generally slower to use loops than recursive functions? There's no general answer to that. Some people might say it's often going to be slower to use recursion because there is an overhead in calling a function, which you don't have in iteration. It depends on the problem and the code. So we've briefly talked about converting recursive functions to tail recursive functions, which eliminates the function calling overhead. And then it should be equivalent. Then it should be the same. But there are problems that just very naturally translate into recursive code, and that would be very difficult to approach in iteration. Okay, this is the summary. For, in, on, across, for, from, to, down, to, by, for being each, hash key, hash value in, so different types of iterations. Even for x equals 42, then incf x. So I can even say how it changes from step to step. Accumulation, collect, append, sum, minimize, count. How often did this happen? control, while, until, repeat, when, unless, and this is not the end. They're more local variables with initially, finally, things that happen just as I start the iteration and that happen after the iteration actually completed. All of these I can package into one loop statement. And they can be combined freely, and something to remember, a common mistake that I also still make is if you don't use any of these accumulator statements, if you don't say I want the result to be some collection or some sum, then loop will actually not return anything. Then it will just return nil as I wasn't told to give you an interesting return value. So it's important to also, often we focus on how do we want to control the iteration and everything, but we also need to say what do we want the return value to be. All right, with that, let me briefly talk about input and output. This is very mundane, something you know, as in most all programming languages probably, input and output to files, to and from files or to the terminal, mediated through streams. The symbol T is again overloaded. So we've already seen it as the truth value, the Boolean truth value true. You can also use it as a stream that will refer to the name of a stream that will go to the terminal. And so often when we're doing printouts for debugging, then we send those to the stream T so that we actually see what is printed. So format takes a so-called format string, so it's like printf. Tilde inserts something at that position in the string. A just means argument. We don't need to say this is a number or something else. It just means whatever that object and its type inserted appropriately at this position. Tilde %sign means new line. That's all we need to know. So format string, 2 additional arguments, and they go into the tilde A positions into that string. We'll often use this curly arrow to distinguish between something being printed out, written to the terminal, from something being returned. Format is the kind of function that we call for its side effect, not for its value. Because everything evaluates to something in Lisp, it's by convention defined to always return nil. Format does never return anything interesting. We only ever call it for the side effect, for something printed to appear somewhere. But that's not the value of format, that's the side effect, and hence the curly arrow indicates side effects. Yes, or printout in fact. So there are other ways of producing output, so write char, write string, and they are the lower level output functions that format will use to generate its. So there's more than one way to do it, but this will serve our needs at least initially. Input. There's a family of read functions, and read line takes a stream as its argument and will read one line of text that is up to a new line from that stream and return that line as a string. Read is not line oriented, it's S expression oriented. So that's what we use to read Lisp data or code, things that are valid Lisp syntax. Takes a stream, and I'll talk about this nil argument in a second, and returns that object. So if the thing that it sees begins with a parenthesis, it will read a list, and it will stop when it encounters the closing parenthesis. If the thing starts with a double quote, it will read a string. If the thing starts with a digit, it will read a number, and it will return different types of objects. So read returns whatever object it actually encountered. Read line always returns a string up to the new line. So the second reader argument here asks to return nil when an end of file is encountered. So here I get to say, often we make that the keyword : EOF. What should read return to me to signal that I'm at the end of this. There's nothing more to read. Finally, how do I create a stream? I need to open a file, and again, something that is becoming more common in the past decade or so in other programming languages. I don't need to setf stream open file. I can do that and then remember to close the stream. There's a special form that will open a file and bind a stream to the stream that is connected to that file, and then that will be valid for the body of this with open file special form. So here is the name of a file. Here I say direction input. I could say direction output. These are keyword symbols. They evaluate to themselves. I use them here to tell with open file whether this should be a stream going that direction or this direction, whether it should read or write to the file. And stream here is a local variable. It's a symbol that will be bound to that stream in the body of the with open file. So the file will be opened, the stream will be bound to this symbol stream. It's the name of the stream. Then I can do something. Often I'll read all of the lines from the file. For line equals read line. While line. So I say read line, second argument nil. So that means read line will return strings until it reaches the end of the file. Then it will return nil. Nil is not a truth value. Well, nil is a truth value, that means false. Nil is not true. So at that point, when I reach the end of the file, while line will become false. Well, the loop will terminate. This is kind of idiomatic, common way of doing this. This just is like the Unix cat utility. It writes out all of the lines in sequence. Yes? Until null of line would be equivalent. So was a question in the break. So at the end of the file, line, that local iteration variable in the loop, will have the value nil, right? Because that's what I say, read line shall return when it reaches end of file. And so while line is a fairly compact way of saying while line is not the empty list or nil, which again is a compact way of saying while not EQ line nil. Can you read this? No. You can't read that over there, but I can type it. Oh. So while line, I said, is equivalent to while not null line. Null is a predefined predicate that tests its argument for being nil, which is equivalent to while not EQ line nil, so which would be equivalent to until not line, for example. Or I think the most intuitive would be to maybe write it like this. So while line or until null of line would be equivalent. So what would happen if I have an empty line, by which you mean? A line where there is only an end of line character, a new line character. Yeah, what should readLine return in that case? It returns that line, it reads one line of text from a stream, returning it as a string. 27 spaces. Why would it do that? Were there any spaces on that line? No, you said it was empty, so it should return the empty string. And it will. So that line was, there were no characters on that line before the end of line, the new line character, and so the corresponding string to that line is the empty string. That's a string not containing any characters. But that is different from the empty list nil. Okay, so this was, I wanted to talk about arrays. I think I'll actually not do that today, and you'll have to introduce some data structures with the, anyway, then you inherit this slide. Okay, yeah, I think I had forgotten about this. So these are more data structures. I mean, I think I'll post the slides as they are, and you can read about them in the Cybele book, and I think Mohav will briefly introduce more data structures as they become useful to us. We want to, at this point, wrap up this crash course in Common Lisp and start doing machine learning. Start actually using the language. You're master students after all. And so ran out of time to presenting this one last week. Enjoy at your own leisure. A few suggestions on good style. And this sort of functional decomposition is an important principle. Try to write small functions whenever you find that you repeat a sub-expression more than once. Consider moving that sub-expression into its function of its own right. Don't be afraid of writing many small functions. One fact, one place. So you shouldn't just copy and paste very similar code and have it in different contexts. Think about what we call abstraction barriers, abstract data types. Promote code reuse is essentially what I said here. So anything that, any piece of code that could be useful in more than one context should be a function of its own and should be called as a function. Much more mundane, we recommend that you limit yourself to 80 characters on each line. White space, so white space or new line, no difference. You can write as wide as you want, but we find that very hard to read. A very strong recommendation, don't put the closing parens on a line by their own, as a C++ programmer might be tempted to do, maybe even a Java programmer. The closing parens go behind the expression that they close. And use indentation to make clear, so indentation is not meaningful, unlike in Python, but it's still very helpful. And Emacs, you can hit the tab character. I think any editor, if it has a Lisp syntax sensitive mode, will indent for you. And that makes it a lot easier to read your code. So next week, Mohav will start on distributional semantics, the first basic machine learning technique. And have we posted reading for that already? We have. So there's a recommended, it's more than recommended, a required reading, something that we ask you to have looked through before next week's lecture.